Hello everyone, welcome back to my solution for 2024 AMC 10A. I was actually going to make this video for yesterday, but as I mentioned, I was busy preparing for the test on Saturday, so it is quite of an excuse, but I couldn't film it. So that's why I'm doing it today. And because we did until 22, let's do from 23. Integers a, b, need to find the value of ab plus bc plus ca. I think one obvious thing that we can do is just add all of them together. Plus ca equals 247. But we need to find this value, and I don't think it will be really helpful because we have a, b, c here, and when we square them we have a squared, b squared, and c squared, so I don't think that's going to be really helpful. Why don't we multiplying will lead us to not good result. Why don't we try and subtract them? Because when we subtract them, then we have prime number, and we can use the information that a, b, and c are integers. So let's subtract these two first. We have ab plus c minus bc minus a equals 13. And if magically factors. So we have a minus c times b minus 1 equals 13. That's our first equation. We can do these two. bc plus a minus ca minus b equals 17. AB, so b minus a minus b minus a equals 17. So we have b minus a times c minus 1 equals 17. That's our second equation. And lastly, let's do these two. So we have ab plus c minus ca minus b equals 40. And this is c. So we have b minus c times a minus 1 equals 40. That is our third equation. I want to try trial and error, and that is because 13, 17, they are prime numbers, and we only have 4 cases. So let me demonstrate what that means. So we have, I'll write it here, and a minus c times b minus 1 equals 13. Now this can be 1, 13, or this can be 13 and 1. This can be negative 1, negative 13, and negative 13 and negative 1. This case, sorry, b equals 14 here, b equals 2, b equals negative 12, and b equals 0 here. Should we try from b equals 0? I think it's easier to eliminate the easier ones first. So if b equals 0, notice that c equals 100, a equals 87, and 87 times 100 plus 0 is not 60, so we can exclude this case. Let's try b equals 2. That sounds quite reasonable. Or b equals 14, maybe. I think b might be equal to 14, so that's why let's try this one first. Then b equals 14, a minus c equals 1, so we have a minus c equals 1, b equals 14. Let's use our second one because we have 17 here. 14 minus a times c minus 1 equals 17. And now that a minus c equals 1, we know that c minus 1 is equal to a minus 2, right? Equals 17. But does this work? A squared 16a was 28 plus 17, 45, right? We have 9 and 5, that doesn't work. 3 and 15, that also doesn't work. 64 minus 45 equals 19. So this so this case does not work. The next reasonable choice is when b is equal to 2. So when b is equal to 2, a minus c equals 13, and b is equal to 2. Using our second one again, we have 2 minus a times, what is c minus 1? It's a minus 14. We have a squared minus 16a. What is 28 plus is 30 and 45? Wait, we have the same. We have the same equation, so this one doesn't work. Then naturally, b must be negative 12. Let's fact check that. We have c minus 1, and what is c minus 1? It's simply a. So a squared plus 12a plus 17 equals 0. Oh, that's quite strange. It should work. Wait, this one doesn't work. It doesn't make sense. It should work. Did we do something wrong? Wait. Wait. Let's check our equations again. Because there's no other. Okay, when we subtract our first two equations, we have we have b times a minus c. Yeah, it is right. There's nothing wrong with it. And second one equals 17. Oh, it's not 17. It's 27. It's 27, that's why. Oh, it's 27. It's 27. Oh my goodness. So you have 27 here, 27. Let's change everything. If you have 27 here. Okay, so, but even if this thing is equal to 27 and b is equal to 0, it will not change anything. 9 and 3, yeah, this works here. And I'm pretty sure it will not work because if both of them works, then we will have multiple answers, and that's not how I think problem makers for AMC makes their problems. But if you want to be more precise, then I think let's just wait, we said 17 and 27, so it should be 55, like when we do it. Wait, 55 it also works? Oh wait, good thing we checked it. So these two, they are the same equation, so we don't really have to worry a lot. 5a minus 11 equals 0, so a is equal to 5 or 11. In this case, a is equal to negative 3 or negative 9. Okay, so we have to check them. So we have multiple cases here. First case, we have a equals 5, b equals 14. The second case, we have a equals 11, b equals 14. Next one, negative 3. And wait, which one is this one? Is it when b equals, it's when b equals 14, right? 14, I'll erase them. B equals 14. Wait, 14? No, it's when 12, right? Negative 12, right? Yeah, negative 12. And negative 9 and negative 12. Now, we just need to check for C. When this is true, then our value of C will be it's negative 1, so A plus 1, so we have C equals 6, 12 here. In this case, wait, we also have this case too, right? When B is equal to 2. Then we will have multiple answers. Uh, 28 plus 45. Oh wait, it is 45. 28. Oh wait, sorry, 55. And this one is the same case, so it works too. I won't rewrite it. But it's quite strange that we get multiple values for. So you have A equals negative 3, negative 9, 5, 11, and 5, 11. We have 6 cases in total. And in each cases, B is equal to 2 for these. And it's negative 12. This one should be 14. Now let's calculate the value of C. Maybe we get some extraneous solutions because we only used 2 of our equations. We didn't use our last one. Wait, did we? No, we did use every equation. But we might get some extraneous solutions. And so when A is equal to negative 13, it's just 3, it's negative 3, not negative 13. So yeah, when A equals negative 3, what is C? C is A plus 1, so it's negative 2, negative 8. When B is equal to 2, A minus C equals 13, so it should be minus 13. So we have negative 2, negative 8 here. And this one, we have A minus C, so C is equal to A minus 1. Why do we have 2? Oh, okay, 4 and 10. Now, obviously, wait, let's check this. We need to try and substitute. We need to try substituting. We have 6 cases. And we need to look out for some extraneous solution that we get. 36 minus 2 is definitely not 100. This is definitely not true. Not true. Not true. 70, not true. Wait, all of our solutions that we found is not true here. And maybe we get some from here because we didn't try them. No, but it will not work anyways when B is equal to 0. Something is really off with our equation. BC plus A minus C minus B equals 27. It's 27. Okay, so this case you can just exclude them. A minus B equals B equals 14. These are correct. I'm not sure where we're getting our errors, but I think we need to check them again. 14 minus A minus C minus 1 equals 27. And what is C? C minus 1 is equal to a minus 2, so this is also true. Uh, 28, 40, 55. It's really strange because everything should be true right now. Yes, nothing is wrong. When b is equal to 2, we have 2 minus, and what is, yeah, so it is also right. We have 5 and 11. What is the value of c? In this case, c is a minus 13. Minus 13, minus 13. It is also true. That means we might have some error in our first case, where we set that b is equal to negative 12. When b is equal to negative 12, c minus 1 is equal to a. So, 12a. A plus 3, a plus 9. So, a is negative 3 or negative 9. And c is equal to a plus 1. I mean, yeah, a plus 1. So they are all correct. There's nothing wrong with our calculation, but what is leading us to our error? Oh wait. I think this case works actually, because I thought 9 times 12 was 98 for some reason. It's actually 108. 100, oh, so it works. These two, we get 96 minus that is 87. We have 72 minus, oh, so what? So this case actually works. Then we have 108 plus 96 plus 72 equals 180, 200, yeah, these are answer. Oh, my calculation error led to a big problem, so let's check if we got it right. I got D. Yay, so it is right, but how did they solve it? Oh, they added? Oh, wait, we can do this. Wait, there are 3 order pairs? I didn't know that. I think this one. I'm not sure. I don't think they use the brute force method that we used, but I think this is the most similar thing that we did. Okay, so that was new, number 24. A bee is moving in 3-dimensional space. A fair 6-sided die face is rolled. Suppose the bee occupies the point. Okay. Okay. So currently, if you have our x, y, and z here, the point is currently on here. Oh wait, why did I write y there? Supposed to be y and z. Okay, we have x, y, and z here. I don't know, like I want to put x here and y here, but I don't think that's like the convention. So what is the problem? But I don't think the drawing will really help there. So the cases, the total number of cases of traversing four distinct edges of some unique cube is if we have we have 8 choices first. No, 6 choices first, right? Because point here you can travel anywhere, up and down and right. Yes, and then from there, if it moved, then we only have 2 choices left. And from there, we have another 2 choices, and there have another 2 choices. So this is the total number of cases in which the B traverses 4 distinct edges of some unique cube. Now, then the entire probability is simply 6 times 6 times 6 times 6. Now the probability should be the total cases over, the desired cases over total cases. However, I think we need to do something different here. And so we have 27 times 3 equals, okay. So wait, if it travels there. No, actually I don't think this is right. Okay, so our total case is clearly this one, and our desired case, what is our desired case? So we have 6 because it can move anywhere. So assume that it moved without loss of generality. Let's assume that it moved here. Now this has multiple cases. It can either go up, it can either go there, it can either go down. No, we only have 2 cases, right? Oh wait, we actually have 4 cases. And then if it, okay, from the 4 cases there, if it moved here and here without loss of generality. So without loss of generality, let's just say that it moved here and there. Now that means this guy has 1, 2, and 3 choices here. Now also without loss of generality, because I keep on saying without loss of generality, because it will be the same cases for everything. So let's say that it moved up. Then the only choices left are this and this. So this is our cases. Okay. 27. But we are starting to consider the probability, right? So we have okay, so what is the probability of making our first choice? It is simply 6 over 6, that is 1. What is the probability of... No, but if we do that, I just simply calculate it and we don't get our answer here. I should get 1 over... Wait, do we need to multiply by 1 over 6? 1, and it has the other 2 choices. One, 2. Wait, we have 1, 2, 3, and 4. it just shouldn't go further. 1, 2, and 3, right? It just shouldn't go there, there, and there. Okay, here we only have 1, 2, right? It just shouldn't go 1, 2, 3, and 4. Yeah, so our cases, we counted them correctly. 4 distinct edges. I think, oh, okay, so this is our total outcome. This is what we want. Three times 3 equals 9. No, I think I can guess the answer. I think the answer is A, choice A. That's because if we multiply 1 over 9 by... So we have 1 over 9 here, and the only reasonable way to get one of these answers are is A. So during the test, I will just choose A because I would think like, oh, I missed a case where I need to multiply the whole thing by 1 over 6. But because we're here to solve it, actually, I think let's think more. So how do we find the probability? You know what? Actually, I think this should be the answer. Oops. This one should be the answer. I'm not sure why I'm not getting them. Plus 1 over 9. We should get, because, and the reason why I say that is because we have 1 over 6. So we have total of 6 times 4 times 3 times 2 cases, and the probability of each case is 1 over 6 because it's a fair 6-sided die. That means our answer should be 1 over 9. However, 1 over 9 is not one of our answer choice, and I'm guessing. Okay, let's try and draw them more clearly. So, assuming that here is 0, 0, it can either go here, it can either go here, or here. How should I draw them? Here, 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 or here. It doesn't really matter. Now let's just say that it landed on here. Then using our red color, this is where it went. Now it has 3 other cases. I'll color the cases in green. It can either go here, it can either go there, or it can either go here, or even here. So we have 4. Now let's say that it went this way, just for convenience, this way. Now here it has more cases. It can either go further back, it can either go down and meet here, or it can either go here, like front. There's nothing wrong with going. So it just should not go here, here, or here. So we have other 3 cases. Now let's say that it went here for convenience. Now for the last case, we have only 2 choices. What is the probability that the 4 distinct edges? It can either go here, can either go there. It cannot go down, it cannot go here, it cannot go up again. It can go... Oh wait, it can go here. It can go here, right? It can go here, can go there. It just cannot go down and up and right. Oh, so I made a mistake. It should be 6 times. Oh, it should be 6 times 4, was it 4? 4 times 3 times 3 over 6 times 6 times 6 times 6. Now this one cancels. This is just simply equal to 6 squared. So our answer should be C. Now let's check if we got it right. I'm pretty sure it is right. I'm not good at counting, but... Wait, what? It is wrong? Wait, before I look at the solution, let me try it again. Why we got our answer wrong? Or I got it wrong? Wait, but how do you get 7? The 7 is so random. So let's check if we counted them wrong. So we have 6 choices. In the first one, we have 1, 2, 3, and 4. And it will be the same because it will just be rotation and symmetric and stuff. So we have 1, 2. Wait, did I miss something from the problem? 4 rotating edges. It is right. So 1, 2, 3, 4. Ended up here, then it should not go back, it should not go up, so we have only 4 choices. Wait. Wait, it should not go up, it should not go that way, it should not... Wait, so it's actually 3. It is right. Now, if it ended up here, then it might change our situation. It can go here, here. Oh, that's why. It's not... I miscounted something. So until 6 times 4 times 3, there's nothing wrong with this. Until here, it should be fine. But, no, actually I will say until 6 times 4. It will be the same until now. But from here, so we have 2 choices from here. If it can either go down, if it goes down, we have 3 more choices. And if it goes this way, we have 2 choices and 2 choices from here. There's no other choice. So the total probability is 6 times 4 times 1 plus 3 plus 2 times 2, which is 7 times 6 times 4. And dividing by 6 times 6 times 6 times 6, we have 3 times 3 and 6. We have 7 over 54. Oh, so the answer is indeed B. I couldn't split them here, and that was my mistake. So let's check how others solved this problem. I don't see the diagram, but anyhow. I think the solution number 1 is same as the one that I had, but the solution number 1 calculated directly with probability, but I counted with cases, and then use probability. So yeah, it's the same. Number 25. The figure below shows a dotted grid 8 cells wide and 3 cells 1 inch closed loop that does not interact itself. Wait, the numbers in the cell indicate the number of sides of the, okay. And any number, okay. I think I might know how to solve this one. So let's say that a guy places toothpick here. He cannot put it here, so should put it here. And if it put it here, it can put it here and there and there. Now, how do we form a loop? This is definitely not a loop. No, this doesn't work because this end and this end does not connect each other. Now, one thing that we can try is maybe this. But this thing is also a problem because we can, then what we can do here is, because this thing, wait, we need to touch it. Okay, so we touched ones here. Maybe we can come back and touch them at the top. So we go like this way. Yeah, this should be fine. Yeah, this is one loop. No, I think it's just binary. It's quite simple. So let's look. How many? 2 to the power of 8. Then it's 2 to the power of 8. And the reason why I say that is each 2 represents whether it touches here or here. But if it touches the top, so what I mean by this is it can go like this one. It can go like this too, right? And that's also included in this case. However, notice that our situation is quite different for our n blocks. And the reason is because it must either touch here or here. If not, then if it touches bottom, then there's no way to go up. Because if it goes up here, then this touches 2 edges. So ideally it should have been 2 to the power of 8, but let's consider more. So excluding the edges, we have 2 to the power of 6. Now, let's say that our first case, it's actually quite simple. So for edges, it will be either this one, or this one, or this one, or this one. Then, should we calculate how many? Okay, so first case, when this touches here and here, then what is our probability? Is 1, 2, 3, 4, right? So 2 to the power 4. And our second case is when it touches this one and this one. Then it should go 1, 2, 3, 4, 1, 2, 3, 4, 5. So it should be plus 2 to the power 5, but we can multiply it by 2 because notice that this case and this case, they're the same. And the last case is when they both touch the edges. So this case, we have 2 to the power of 6. Yeah, so let's calculate that. 16 plus, what is 2 to the power of 6? 64 and 128, we multiply them by 2. So our answer should be 144, which is B. Oh, it's number 25 and it's easier than what I thought. Wait, but I might get it wrong, so let's check it. Please. What is our answer? Wait, where did I miss the two cases? That's why it's number 25. I missed two cases. Oh, I found it. Are we missing? Oh, wait. No, I cannot revert it. Undo? Oh, wait, I can. So I think the cases that I missed is this one. The case when no, but oh, okay. This case, we missed this case. This one in here. So you should add 2 and get 146. Our answer is C. Oh my goodness. That's why it's number 25. I missed the last two cases. I fell into their trap. Let's see how they solved it. Why can't I see the images? Same method. Yeah, but we forgot the last two. Yeah. Okay, so. Oh, I think my solution was the same one as solution number 1. This was the complete solution to 2024 AMC 10A. It took more than what I expected because I had to explain, and for the next one, I will try to reduce time. I hope you enjoyed my personal solutions to 2024 AMC 10A problems. If you want me to try different problems, please tell me or comment down in the below. I think I can try until AME. USAMO, to be honest, USAMO, KMO, they're quite hard, so I think I can try the live virtual solutions until AME level. So thank you for watching the video and the series. Thank you, and see you again today with my another Olympiad series. Thank you and bye.